Gentlemen, will you please take your seats so we can begin today's conference? I take a great deal of pleasure in presenting to you today as our guest speaker, Dr. Werner von Braun. Dr. Braun.
Gentlemen, the conquest of outer space is the greatest technological challenge of the age in which we live. The first decisive step in the conquest of space will be the placing of an object into an orbit wherein it will indefinitely circle the Earth. It takes a speed of approximately 18,000 miles per hour to accomplish this. And this is approximately 3 times the greatest speed ever attained by rockets today. How can we reach such a speed? First of all, of course, one could think of improving propellants used in present-day rockets. Secondly, we could shave some weights off our designs. But with both these methods, it does not appear possible to gain more than approximately 40 or 50% of the speeds that rockets reach today. A fundamental step ahead in increasing the speed will be the application of the multi-stage principle. Let us take a look at our first slide. Through the ballistic trajectory, you have weightlessness. Such a long 3-minute weightless ballistic parabola is shown in the upper part of this picture. The next slide shows what happens inside an airplane flown through such a ballistic trajectory. You see a little matchbox floating in the left upper corner of the canopy. This matchbox was released by the passenger in this flight and was photographed by him to show that the matchbox is actually floating freely in the canopy, and it floated there for approximately 40 seconds. In fact, pilots who have repeatedly flown through such ballistic trajectories even use such free-floating objects to make sure that they are right under the weightless condition. If they apply a positive or a negative lift, the matchbox will come up and down. If they have too little or too much thrust, so that they either under or overcompensate the aerodynamic drag, the matchbox will move fore or aft. This condition, which, as I said, can be simulated for 40 seconds now and for maybe 3 minutes with advanced rocket airplanes, will be a permanent experience in any orbiting rocket ship. What will happen when man is subjected to this condition? Well, we know that a man can eat and drink even in a horizontal position, and if you try it, you find that you can even eat upside down. Will the blood circulation be affected? Medical doctors think that it will not, because the most important factor in the blood circulation is the drag, the resistance of the blood in the veins and the arteries. And gravity plays only a minor part in it. Well, in fact, you can lie horizontally in your bed and you can get up and your heart circulation is hardly affected. But nobody knows today how extended weightlessness will affect people. Some doctors believe the most critical question will be the sense of equilibrium in the inner ear. There's a little pebble in the inner ear, both inner ears, called the otholites, which rests on some hairs, and on whichever hairs they rest is an indication this is down. If you move your head forward, that pebble moves on another set of hairs, and you have a different indication of the plumb bob direction. Under weightless conditions, this pebble, of course, is disoriented and it simply floats without touching any hair, or may erratically touch a hair here and a hair there. And the question is, how will you react? The feeling is some people may get seasick, maybe they can get used to it. In these flights through ballistic trajectories, people have been trained to draw little sketches, and the interesting thing was that the sketches improved after going repeatedly through the experience. So all we can say today is that there is reasonable hope that people can be trained and accustomed to this unique condition of weightlessness. So you see, this weightless condition actually exists in a rocket flying unpowered outside of the atmosphere. Now, what happens when our ship gets into the orbit? On this picture, we have assumed that the ship took off from an island in the Pacific and climbs into an orbit which is inclined under about 65 degrees to the equator. So the the ascent is on a northeasterly course. Shortly after having left the island, in fact about 1,000 miles downrange, the last stage has reached terminal velocity. But since it has an excess velocity over and above circular orbital speed at that altitude, it now recedes further away from the Earth unpowered and reaches the apogee just 180 degrees on the right upper corner of this globe. If we want to establish our rocket in a circular orbit at this altitude, 1,070 miles up, we have to provide a little extra kick in this apogee to prevent the rocket from going down to the perigee altitude of 60 miles again. This is a minor maneuver requiring only about 15 seconds of power application. After we have given the third stage this extra kick, it is now permanently established in a circular orbit 1,075 miles up. This picture here shows the interaction between such an orbit and the rotation of the Earth. In a 1,075-mile orbit, the ship will go around the Earth once every 2 hours. But the Earth itself will rotate inside the orbit at a rate of 1 revolution in 24 hours. As a result, the orbiting station will pass the equator each time at a different meridian. And an observer in the ship will see different portions of the Earth overflown during a period of 24 hours. In fact, within a period of 24 hours, he will have the opportunity to see every point on Earth at least once. And this is one of the reasons why I believe that such a manned orbital station will have a terrific military importance, both as a reconnaissance station and possibly even as a bombing platform. It has been suggested to build a manned space station in such an orbit, 1,075 miles up, a 2-hour orbit. But before one could build such a station, it would be necessary to provide facilities or equipment so that people can leave their orbiting ship. Since the orbit lies in the vacuum of outer space, it would be necessary for anyone to leave the ship to don a pressurized suit. The man is essentially garbed into a fiber-reinforced rubber suit with flexible joints, and it is possible to walk with such a suit, although there is 1/2 of normal atmospheric pressure inside the suit. It is questionable, however, whether such a suit fashioned after the human shape is quite ideal for assembly operations to be performed in an orbit. In the first place, in order to build something, you usually don't need your feet, but only your hands. And secondly, you have to use quite complicated tools to do a decent assembly job in an orbit. For this reason, I believe that spacesuits to be used for such orbital assembly work may actually look quite different. The next slide shows what they might look like. This is actually no longer a suit. It looks more like a Coke bottle. It is a rigid container which is pressurized inside with a man looking out through a glassed dome at the top. The operator would be strapped to a kind of a couch inside this bottle and can turn himself around within the bottle. In front of the couch inside this bottle and can turn himself around within the bottle. In front of him will be a whole panel of instruments through which he can operate these artificial arms that you see sticking out from the bottle. The arms can be retracted, and at the end of each arm can be a different kind of tool. It may be a hook, or it may be a drilling head with various gauge drills, or there may be pliers, or wrenches, and so forth. The entire system would be fashioned after, shall we say, the method of operating amputees' arms. The man could move himself around by built-in gyroscopes, which he can control with a steering stick, so as to acquire any spatial attitude he wishes by just using the precession forces of the gyros. There will also be 2 small rocket motors, one on top of his canopy and the other at the bottom of the bottle, which could be used for transversal motions. The thrusts required would be only in the order of a few pounds. With such equipment, we could seriously think of assembling an orbital station. Now, what will such an orbital station look like? I don't know. Maybe it is smarter to build a number of small ones. Maybe we want to clamp a lot of equipment into a large station. This is immaterial. On the right side of this picture, you see a large wheel-shaped space station, which should be construed more or less as a proposal as to what you could possibly do with a space station, and it is not necessarily a proposal that a space station must look exactly like the thing, in particular must be that large. In fact, it can be a lot smaller if you want to reduce the equipment aboard or prefer to have several smaller ones. The wheel shape has been chosen for the purpose of doing away with the permanent weightless condition prevailing in the orbit. By putting a spin on such a wheel, you could provide an artificial or synthetic gravity in the rim. The wheel would simply spin slowly about its hub, and by putting the right spin on, you can either simulate 1g acceleration in the rim or 1/3 of a g if that's considered sufficient. At any rate, you can give people their weight back. The people, of course, would live in the rim. Now, how would it be possible to build such a large station in an orbit, and how could we bring the equipment up to do this? The cargo holds in even large rocket ships will always be limited, so one of the most important things will be that you can ship the parts up small enough so they can be stowed away in the cargo holds. One way of doing it would be to fold them together. And in this particular proposal, I had envisioned to build the space station of 10 or 15 segments of rubber impregnated fiberglass or some material similar to that used in rubber floats or rubber rafts, and put the ring-shaped space station together from these sections. After the assembly has been completed and all the sections have been joined together, the entire unit can be inflated like an automobile tire, and this would provide not only the necessary rigidity to the structure, but also the atmosphere within the tire in which people could live. Of course, for an extended stay, it would be necessary to replenish the air and provide an air conditioning system, an oxygen replenishing system, and CO2 removal system in the station. Inside, such a space station may contain all sorts of equipment. There will be laboratories in the rim where phenomena can be studied which are not accessible to experimentation on the ground. Such experiments may include questions involving biological and zoological life under the conditions of outer space, cosmic radiation, meteorological research, whereby the Earth can be observed from the outside, astronomical laboratories, etc. Close to the space station, there will be a powerful telescope. If you aim this telescope at the heavens, you can see the planets unblurred by atmospheric effects, and we can expect to be able to take photographs of planets like Mars or Jupiter with unprecedented clarity. If you turn the same telescope to the ground, you would be able to distinguish as much detail as you can see from a plane, say 4,000 or 5,000 feet up. This, of course, offers tremendous possibilities to reconnaissance, and both reconnaissance in the civilian sense as in the military sense. The civilian reconnaissance, I mean iceberg warnings could be flashed to ships, expeditions could be observed as they proceed over the Arctic plains, and military reconnaissance, of course, means that you could keep a watchful eye on countries not accessible with aerial reconnaissance aircraft. As far as the military application of the station is concerned, it seems even feasible to use such a platform in space as a base for the bombing of objects on the ground. And it is my opinion that such bombing could be carried out with an unprecedented accuracy from such a station. The most important application of a space station, however, will be that it can serve as a jump off. Once we are in the orbit, we can disregard a lot of the requirements required for rockets capable of ascending to an orbit. In the first place, we can completely forget about aerodynamic drag and streamlining, because any flights into deeper space will be outside of the atmosphere. Secondly, once we have attained orbital flight, we can break away from such an orbit and go out into deeper space with very low thrust ratings. The reason for this is simple. The weight of any ship circling in the orbit is already sustained by the centrifugal force in the orbit. So any pound of thrust you apply to an orbiting object in the right direction will enhance the speed and therefore carry the object further away from the Earth. And such acceleration of deep space ships can be carried out virtually micro G's of acceleration. This is a great difference from takeoff from the ground, where it is obvious that you have to have a thrust that exceeds the weight of the ship simply to lift it off the ground. For example, a trip from a space station around the moon and back to the space station would look something like this. It would simply be a wingless hull made up of an upper stage of a three-stage surface-to-orbit spaceship or rocket ship, and it would be surrounded with a string of 7 peripheral tanks which simply add fuel to this vehicle. And with one little weak engine in the rear, we can power this ship to fly all the way from the space station around the moon and induce it back into the space station's orbit. We will get used to forms like this in the future when we are talking about deep space ships. Of course, before we can fly people to the orbit, it would be necessary to provide ways and means of returning people. And it is my opinion that the return from an orbit is a task much more formidable than attainment of orbital flight itself. In other words, the problem of hurling a small object or even an instrumented object into a satellite orbit that is not Earth returnable is essentially a question of brute force. But to return people safely from an orbit is a question that involves all faculties of modern physical science. The reason for this is simple. We cannot afford to land a spaceship from an orbit by slowing it down from its orbital speed with propellants. The reason for this is easy to see. We have to destroy the same energy on the way down that we imparted on the object to bring it up there in the first place. This would mean we roughly would need the same amount of propellants to land a ship with rocket power alone than it was necessary to bring it up there. And of course, this fuel would constitute payload for the ascent, so initially the ship must be much larger if it were to carry enough fuel for the descent. But there's a shortcut to this problem. If we depend on aerodynamic deceleration during the descent, we can put the atmosphere to use to slow us down again. But this means that the ship must re-enter the atmosphere at a speed comparable to the orbital speed of 18,000 miles per hour, and from this speed we must gradually slow the ship down again. And this creates a formidable aerodynamic heating problem. Of course, if we would descend at these high speeds directly into the deeper layers of the atmosphere, our ship would obviously burn up, and we wouldn't have a chance of building it sturdy enough and in such fashion that people could survive the trip. But if we equip the ship with wings, we can glide it out. We can retard the ship at very high altitudes where the density isn't high enough to create too much heat flux, and we simply radiate the heat out from the wings. The ship will still get pretty hot in the process, but we can keep it at the high altitudes provided our wings are large enough. Now this is the upper stage of an orbital ship as would be required to come down. The amazing thing about such Earth-returnable winged upper stages is that their landing speed would be extremely low. In fact, this ship would land at something like 60 miles an hour. It is not that we couldn't make it land faster, but we have to provide it with relatively large wings in order to be able to decelerate it at sufficiently high altitudes. So it is the heating problem that governs the wing size and not the landing speed. And when you figure it out, it so happens that the wing loading must be so low to achieve this that the landing speed of this empty can with no fuel aboard and just the passengers aboard would be so low that the landing speed is actually in the order of 60 miles an hour. This then would terminate the trip to the orbit. On the approach to the landing field, the ship would run out a tricycle landing gear and finally land on the strip like a normal airplane. Thank you.
Gentlemen, Dr. von Braun has kindly consented to answer any questions you may have, and I presume that you'll have lots of them. Colonel Ablett, would you like to take the first question?
Doctor, in the book, Across the Space Frontier, of which you are co-author, it states that a powerful telescope can keep under inspection every ocean, country, and city just as an observation plane at 4,000 feet. In another place, it states that to the naked eye, the day side of the Earth appears as glaring white patches of overcast resulting from the light of the sun. It appears that an inspection of military value is most questionable at 1,000 miles and above. Would you comment on this capability, please?
I think the emphasis of your question is on the word overcast. Photographic reconnaissance through an overcast is impossible with optical means from an aircraft as much as from a space station. And the glaring white patches refer to the overcast, not to the clear areas on the Earth. As far as photographing through the atmosphere from 1,000 miles is concerned, we think that you will get a very high-quality photographs. The reason is the following. Even astronomical telescopes have to photograph through the atmosphere, but there the atmosphere is within and in a very short distance from the telescope, so all that little atmospheric turbulence is right in the vicinity or even within the instrument itself, and therefore really blurs the picture. When you take photographs with a similar optical system from outer space inside the atmosphere, those atmospheric disturbances and turbulences are far away, and the atmosphere is actually a lot more transparent from the outside than it is from underneath. You may be able to compare the situation with a piece of oil paper. If you hold it close in front of your face, it's opaque. Whereas if you hold it on a piece of newsprint, it is perfectly transparent. You have very much the same situation here. So I believe the quality of the photographic pictures taken with powerful optical systems from an orbit will actually be quite good.
Commander Finn, do you have a question?
Dr. von Braun, it has been said that you could bomb the Earth with extreme accuracy from a space satellite, say with guided missiles. Would you, within the classification, explain why it would be easier to bomb New York from a satellite than from, say, a plane or a land-launched guided missile?
Let me make a little sketch to explain the problem. Suppose this here is the Earth, and this is an orbit around the Earth to which the space station is traveling in this direction. Now, if you fire a guided missile backwards from the space station, imparting upon it something like 400 meters per second, or approximately 1,000 feet per second, in the opposite direction, then the total speed of this missile will be 18,000 miles per hour minus that little velocity you imparted in the opposite direction. As a result, your guided missile will still go through an orbit, but this orbit will be an elliptical orbit. And you can choose a velocity here where this perigee point here just fringes the upper layers of the atmosphere. Now, it is important to note that during this entire flight through this ellipse of descent of the guided missile, the space station and missile will always be very close together because they are both going along like this. At this point here, where the perigee is reached, the missile will be a little bit ahead of the space station because its period of half revolution, the time required to travel from here to here, is shorter than for the space station that goes from here to here. As a result, it will be slightly in angularity ahead of the space station. At this point, the station will be here, and the missile will be here. Now the missile begins a glide through the atmosphere. It is a winged missile. It will descend deeper and deeper into the atmosphere. But during this entire flight, the space station will stay overhead. So it can keep track of the missile even during this phase. And since the missile loses speed here, where the space station does not, the space station will catch up angularly with the missile again. So as the target finally comes in view, say this is the target, the space station will still be overhead, and the missile will be here. So during the entire flight of the missile, you maintain a line of sight between the space station of the missile, and as you approach the target, finally, even the target will come in the line of sight. You can see the target and the missile simultaneously. The missile would carry a radar beacon, and either an optical telescope or a radar telescope can be bracketed at the target, and with a little computer in the space station, which would be comparable to a computer in anti-aircraft missiles, you can simply make these two lines of sight match at the moment of impact. Now, this is a method that cannot be used with intercontinental ballistic missiles. You never have the advantage of seeing the target. Here, you have that advantage. So it is even feasible to fire at moving targets, such as ships on the seas, by using this principle. And you need not know the geographic coordinates either, with which some of the people on the other side of the Iron Curtain do not publish, usually. So as long as you see the object and can keep track of your missile by means of a radar beacon, you can shoot at it, even if you don't know the exact location, and even if it's a moving target. Hope this answered your question.
Colonel Sandine, Doctor, will the space platform be vulnerable to rocket attacks from the Earth's surface?
In principle, yes, but I think it would be a lot more difficult to accomplish than may appear at the surface. Let us not forget that the major portion of the ascent of a rocket, whether manned or unmanned, to a space station is an unpowered flight. And you can't apply a target-seeking system to an unpowered rocket. You have to power it to do that. And that's a very inefficient way of going up to the space station. To build a target-seeking rocket to knock out a space station certainly isn't a very simple task. When you have a manned ship approaching a space station, you can carry out active navigation in which the space station itself, with its radio and radar gear, can support your rendezvous maneuver. If you don't get that cooperation from the space station and you have to depend on target-seeking methods, you have to apply power and all the necessary corrections in the unmanned missile, and this is quite a formidable problem. I wouldn't say it can't be done, but it's certainly very difficult.
Commander Rogers?
Doctor, what system of communications will be used in outer space?
Do you mean communication between the Earth and the space platform?
Yes, between the Earth and the space platform.
Essentially radio. There's only one complication in this radio system, that lies in the fact that the space station travels over a substantial portion of the Earth all the time, and you cannot communicate with any point on Earth all the time with the space station. It requires a whole network of radio stations on the ground, and only a few stations can be in contact with the station at one time. Short waves cross the ionosphere quite easily, and it is an established fact. We have lots of experience in ballistic missiles today to know that we can penetrate the ionosphere quite easily with radio.
Commander Reed?
Doctor, what system of navigation is used to locate a spaceship?
Do you mean navigation for the crew of the ship? In other words, how would the crew navigate its ship to the...
How would you navigate a spaceship from point A to point B in space?
Well, if these points are close together, you could do it optically. You would determine the position of point B to which you are traveling against the background of the stars, determine its position and motion, and then feed the necessary correction into your speed so as to match this point at the predetermined time. Now, if it's a navigation problem over greater distances, such as shall we say, the rendezvous problem of one newly arriving spaceship with a space station, you would apply techniques like taking radar bearings or optical bearings. And if the question is to set up the ship for a return maneuver to the Earth, that you want to land at a certain predetermined spot on the Earth, the emphasis would be on putting the right attitude on the ship for the initial landing maneuver and also time it properly. And this can be done with clocks, signals from the ground, and also with determining your position above the ground, simply by measuring what point you are just passing over from the surface of the Earth. For greater distances from the Earth, star occultation measurements behind the rim of the Earth and the Moon are a very effective way of maneuvering. So I think navigation will be carried out with different means, but most of them will be optically and by means of radar.
Colonel Haberger?
Doctor, what would be the expected lifespan of a spaceship, considering that it might collide with meteorites or dust particles in space, and could any protective means be devised to increase this lifespan?
The question of lifetime and protection go closely together. It is known from shooting star observations that the frequency of abundance of small meteors increases as their size decreases. So the smaller ones are to fear, and the big ones are few and far between in outer space. Now, fortunately, the small ones can be warded off quite easily with a relatively thin armor of dural or metal, or steel. Even the skin of a normal airliner would give you protection against shooting stars up to about 16th magnitude. If you want to have a little more, you may have to use steel to do it. But the weight penalty wouldn't be severe. In fact, the hull itself provides quite a little bit of protection. Dr. Fred Whipple, the Harvard Astronomical Observatory, has always to use so-called meteor bumpers to protect rocket ships and space stations from this meteor danger. The principle of such a meteor bumper is simple. It is nothing but a thin steel or dural skin spaced about an inch or two outside of the inner hull of the rocket or space station. And the meteor impinging upon the surface would simply evaporate due to the impact, and it may put a little dent in the meteor bumper but not harm the surface underneath. If the meteor is large enough to penetrate this bumper, it will explode and rip quite a substantial hole into this thing, because the effect is very much that of a surface explosion on the metal, because all the kinetic energy is immediately transformed into heat. To answer your question of lifetime, we think we can provide protection without an undue weight penalty, shooting stars up to about 12 or maybe 14th magnitude, which still means tiny little particles not larger than a grain of salt. But those are the ones really to fear. With such a protection, it is possible to protect a ship or space station for a period of, say, 5 or 10 years. That is, of course, a statistical figure. It means the likelihood of the penetration would be one penetration in 5 or 10 years. You can easily step this up to 10 years or 100 years or 1,000 years by just providing slightly more material on the meteor bumper. So I think this is not nearly as tricky a problem as the protection of pressurized bombing planes against bullets.
Colonel Sayre?
Dr. Von Braun, in view of our rapid advances in the field of atomic power, do you feel that there's a possibility of utilizing a series of small atomic explosions to propel this rocket out into outer space?
I don't think atomic explosions is the right word, but it is quite conceivable that an atomic reactor-type rocket may someday replace the chemical rocket. As things stand today, however, the chemical rocket still appears to be superior, at least for launchings from the surface of the Earth. The reason is that temperature limits in the reactor itself are quite severe, and in fact you cannot even attain temperatures as high as in a chemical combustion in an atomic reactor due to the limitations posed by the melting points of the materials in the reactor. So the efficiency of a nuclear rocket is not yet as high as that of a chemical rocket. And I'm not saying that it is hopeless to build atomic rockets that can depart from the Earth, but as of today, they can't match the performance of chemical rockets yet.
Doctor, is there any significance in your selection of the 175-mile radius in space for the establishment of this platform?
There's only one practical reason for it, and this is the possibility of continuous contact with a ground base which would support the space station. It is entirely unnecessary for a spaceship that goes up occasionally into an orbit or for an unmanned orbiter to gather some information from the ground. The sole reason for the choice of the 1,075-mile orbit is that the period of revolution in such an orbit will be exactly 2 hours, and these 2 hours are an even fraction of the 24 hours at which the Earth rotates about its own axis. So you can reach the space station from one given base on the ground once per day if you have that condition that the period of revolution is an even fraction of 24 hours. If it were not an even fraction, you may have to wait for a few days before you can make physical contact with the space station again with another ascending rocket.
Colonel Hoover, you look kind of restless with the question.
Dr. von Braun, I'm not completely clear on this business of orbiting here and this apogee. It's been stated that this first satellite, Vanguard, will be put into an elliptical orbit rather than a circular orbit. And it seems, and I don't understand why this is, because it seems to me that as the satellite is nearest the Earth, at that point, its gravitational pull would be greatest. This gravitational pull would, having a difference at various times in the orbit, would have a tendency to unbalance or upset the satellite's orbit. Could you explain that a little more, please?
The circular orbit can actually be considered as a special case of an elliptic orbit, in that a circle is an ellipse where the two foci coincide. And all orbits in the planetary world are actually more or less elliptic. Even the Earth's orbit around the Sun and the Moon's orbit around the Earth are slightly elliptic, but the eccentricity of these ellipses is small. Now, the establishment of a rocket in an exact circular orbit requires very accurate velocity control at cutoff of the last stage. And in the minimum satellite, such elaborate equipment as would be necessary to control the speed to that exactitude would pose an undue burden on the satellite vehicle. So it is a lot simpler to simply give the satellite a slight excess velocity at cutoff of the last stage, which puts it automatically into an elliptic orbit because you have a certain excess of centrifugal force at the cutoff point. Such an elliptic orbit is just as stable as a circular orbit. The only thing that may make a minimum orbiter somewhat unstable lies in the fact that the lowest point of the orbit, the perigee, still fringes the atmosphere and may lose some of its velocity every time it passes through the upper layers of the atmosphere.
Captain Schwartz?
Doctor, would you care to comment on the relationship of Project Vanguard, the satellite program, to the geophysical year?
The geophysical year is an international project which is scheduled for 1957 and 1958, under which a great number of nations have agreed to make a very thorough survey on anything known on the properties of the Earth. Now, the United States government has announced its participation in this international geophysical year, not only with a satellite, but with a lot of other projects. And the satellite has been tied in because it is realized that a satellite, even a very small satellite, can contribute a lot to man's basic knowledge on the property of the Earth. There are other pieces of information. For example, the geodetic survey of such a satellite from various points on Earth simultaneously would improve our knowledge on the location of the continents with respect to each other. I understand that so far the relative location of the Eurasian landmass compared to the American continent is known with an accuracy of approximately only 500 yards. And with a close satellite at low altitudes, a few hundred miles up, it is felt that this could be improved to, shall we say, 10 or 20 yards.
Colonel White?
Doctor, my question has to do with velocities in space. From what I have read and what I have gathered from your discussion here today, I have formulated an opinion that theoretically there is no limit to the speed that man can reach in space. Would you care to comment on this, sir?
As far as rockets are concerned, and they are probably the only conceivable vehicles to build up very great speeds in outer space, there is no practical, no theoretical limit in sight. There is a very definite practical limitation set by the amount of fuel that such a rocket can carry. And it's one of the reasons that the first endeavor will be concentrated upon putting something into an orbit, that this limitation exists. The speed in an orbit is approximately 4 miles per second, the low orbit, and this is about the maximum we think we can get with chemical fuel rockets. Of course, it is conceivable to build rockets that build up higher speeds, but the ratio between the fuel consumed and the payload it can carry becomes less and less, and finally the payload becomes insignificant. Now, at the other end of the ledger, there is a very definite theoretical limit for speed you can attain at all, a physical limit imposed by the laws of nature, and that is the speed of light. Now, that speed is 180,000 miles per second, so we still have a long way to go before this will ever be of any practical significance. The theory of relativity, Dr. Einstein, decrees that no object can exceed the speed of light. The inertia of mass approaches infinity as you approach the speed of light, and therefore it would take an infinite thrust to accelerate anything beyond that speed. So that's the theoretical limit, but as I said, we are still a long way off.
Warner, do you have any more questions?
Doctor, just how far, within the classification of this conference, of course, how far do you think that the Russians or other nations of the world have gotten in this space travel?
Well, it looks like the Russians are very well aware of the capabilities of rockets, both for long-range and anti-aircraft purposes. They certainly realize the feasibility of an orbiter. I believe they are working hard at it, and I still hope that we'll be first up there, of course, but I think we have no time to lose if we want to be first in an orbit.
Well, gentlemen, I'm afraid that time has caught up with us, and we're going to have to terminate this conference. Dr. von Braun, I certainly thank you for a very interesting presentation. Thank you very much. And with that, we have concluded another officers' conference, a discussion of a current and important problem. Our guest today was Dr. Werner von Braun, the noted guided missile and space travel authority. In closing, I would like to remind you that what we have said here today is not necessarily meant to be conclusive, since it is conditioned by our knowledge as of the date of this officers' conference, which is October 20th, 1955. The Officers' Conference Series is produced by the Office of Armed Forces Information and Education of the Department of Defense.